All right, so to finish off this conversation in the first half of this chapter, where we're discussing different tests for convergence or divergence with series, we want to talk about a strategy. So within each particular section of homework problems, you know what test you're applying in essence, right? So when you're doing a section like 11.5, you just learned about the alternating series test, and you're looking to apply that test to the problems in that section. When you've learned in 11.3 about the integral test, you're looking for problems in that section to all be done with the integral test. Now, if you're taking an exam and you're looking at basically a jumble or a collection of problems, you're not told which test to use, then we want to be able to determine, right, which test is best to use. And this reminds me of a technique of integration chapter where in the end you're not sure what technique works and you have to focus on some of the forms to determine which technique would work. And we have the same kind of conversation here. So we don't really want to test a whole lot of series in this conversation. This would be a pretty short video because we've done a whole bunch of examples in prior videos. So I just want to discuss strategy here. Okay, so let's say we're just looking at strategy for testing series. Okay. All right, now usually on a test or in a homework, you don't typically see this exact form of a series like a p-series or a geometric series. But I mean, we're gonna list it, right? So if the series has the form the sum of 1 over n to the p, then this is a known. Then this is a p-series, and the p-series converges for p greater than 1 and diverges for p less than or equal to 1. Now, in most cases, we don't have an exact p-series, and we talked about the comparison test or the limit comparison test. So I'm going to kind of put a little note here. I'm going to say number 2. If the series is a ratio involving, and actually it doesn't even necessarily have to be a ratio. It could be just kind of a polynomial term. But if it is an expression, let me say, if this is an expression that involves really only, I'm going to say polynomial-esque, right, or algebraic types of functions. So if an expression involving algebraic forms, and these are, similar to a p-series, then what we would do is use the, some books call it the direct comparison test, or better yet, we would use the limit comparison test. Okay. All right, so the third one would be, let's say, a geometric series. Now again, usually in the context of a chapter test, we don't have an exact geometric series. We might have something similar to, but just in our summary, right? If the series is geometric, and remember the way that we wrote geometric series was typically like a r to the n minus 1 and goes from 1 to infinity, something along those forms, right? This is really what the geometric series looks like. Okay, plus dot dot dot, right? So as long as the series has that exact form, then it is geometric. So if the series is geometric, and then the common ratio being less than 1, the series converges. Otherwise, if the absolute value of r was greater than 1, the series diverges. Okay. And again, it's rare that we see that exact form. So I would say, little asterisk here. If the expression, right, if the a sub n terms, right, involve exponential forms, and typically when we said exponential forms, we meant things like 2 to the n, or 5 to the n, or 1/2 to the n. Right, so usually when we had exponential forms, I'll say, something like a base to the n power, let's say. So if we had exponential forms, we can use the ratio test. Excuse me. We could use the ratio test. Actually, we could use the ratio test. We could use the limit comparison, or the direct comparison. Those would typically be the best approaches there. Okay. Now, keep in mind for both of these, I'm going to stop for a second. We could also use the integral test in some of these situations. But I reserve the integral test for like my last thought process. So I don't want to have to do an integral if I don't have to. These tests that we're discussing now are a little more straightforward. What happened to my number 1 here? All right, so r is less than 1, it converges, r greater than 1 diverges. All right, and we'll look at a couple specific forms as examples here, right? But just kind of going over the general strategy. Now, something else I would typically want to consider first is the test for divergence, right? So if we can see kind of quickly, without a whole lot of trouble, that the limit of the terms are non-zero, right, then we should use the test for divergence, right? Then we apply the test for divergence. Now again, when we talked about this test back in our video for 11.2, we want to remember that if the terms do go to 0, there is no conclusion here. Right? So I'm going to put a little caution, right? C-A-U-T-I-O-N, right? So caution, if the terms do go to 0, there's really no conclusion, right? That could converge, that could diverge. And we looked at a whole bunch of examples back in that video. So caution about that scenario. Okay, I wanted to scroll for a second there. The next form of test we looked at was the alternating series test. So if the series has the form, it's going to alternate, right? So some books say -1 to the n minus 1 times b sub n goes from 1 to infinity, right? So this makes the first term start positive. We could have the first term start negative. The real thing is that the series is alternating. So what we do then is we look at that b sub n, right? So when we did this test, we looked at just the terms of the series that don't alternate, and we tested that. So as long as it has this form where it alternates, right, then we're going to use the alternating series test. Okay. All right. So then the ratio test we had discussed, and remember the ratio test was really convenient with forms that had factorials or exponential forms. And we could use the ratio test when we have exponential or geometric-esque types of forms, right? So I'll just say something like, for a series with factorial and or exponential forms, then we're going to use the ratio test. Now, just as a reminder that if we have factorials, we're going to solely use the ratio test, right? So any series that has a factorial form in it, this is the default form for the most part. We're going to typically jump to the ratio test. Now we also talked about the root test. So the root test was a real special type of version, a real special type of form. So if we had, if we have the form like, let's say a sub n all raised to the n, right, then we would use the root test. We typically don't see a whole lot of series of that form, but if we do, then that is a very convenient test to utilize there. Right, and then I would say last case in my flow chart that we're discussing here is if it looks like, right, if a sub n, if I consider a sub n as a function where, let's say, the integral is easily done, right, is easily evaluated, let's say, then we're going to use the integral test. All right, now again, I know I've said this already. This is kind of a, worst case scenario. I don't really want to use the integral test if I don't have to, but if it does look like it's a very simple integral I could evaluate, this might be more convenient than some of these prior tests. But if the integral looks challenging, and I'm going to try one of these other tests first. So let's take a look at a couple examples where I just want to discuss strategy here. I don't want to actually test these series. So let's say the first series I want to consider is like n minus 1 over 2n plus 1. Now when I look at this series, even when I do have polynomial forms, I might think of a p-series in this case. I also notice that if I take the limit of this expression, right, I'm going to get 1/2, which is non-zero. So I'm going to jump right to the test for divergence. So I would use the test for divergence here. I probably should have discussed that first up above. That really is the easiest type of test to use. So maybe in my flow chart, looking at the test for divergence first. If I can use the test for divergence, I'm done. Now keep in mind the disadvantage, and it's not that huge of a disadvantage, but if my limit of my terms is equal to 0, then there is no conclusion here, and I would move on and apply a different test. Okay, let's say that we had, and I'm just going to make some kind of wicked looking expression here, said the square root of n cubed plus 1 all over 3n cubed, let's say, plus 4n squared plus 1. And remember, I've talked about this multiple times too, right? It doesn't really matter where my series starts. And it's just that we're looking at infinite series here. So I keep writing n equals 1 to infinity, but I really could leave that bottom initial starting point off. Now when I look at this, what I think of here is I have ratios of algebraic expressions, algebraic functions. So this is most likely going to behave like a p-series of some form. Now remember when we did a comparison test, right? When something behaves like a p-series, we typically use a limit comparison test or a direct comparison test. Now, personally, I liked the limit comparison test when we discussed that in 11.4 because we don't have to dwell on that inequality, right? With the direct comparison, we have to dwell on whether an inequality is true or not. And with the limit comparison, we don't have to dwell on that inequality. We just do a limit of our hunch, right? So I called it taking a hunch. And what we did was we focused on the leading term in the numerator and the leading term in the denominator. And then I would simplify that expression, right? So this is the numerator into the 3/2, then the denominator, really n cubed, right? And when I subtract like exponents there, what do I get? I get 3/2, and minus 3 is minus 6/2. excuse me. So I get into the, let's see, what is that going to be, negative 3 halves? So I really have 1 over n to the positive 3 halves. So this behaves like a convergent, p is 3 halves, that's greater than 1. So this behaves like a convergent p-series, so I would do a limit comparison test for that series. All right, so another example, let's say we look at negative 1 to the n. Let's say we have n cubed over n to the 4th plus 1, let's say. Right, again, doesn't matter where that series starts. We're looking at an infinite series. So when I look at this series, seeing that alternating term kind of screams to me alternating series test. So I'm going to scribble down alternating series test here. Now you also might remember in that prior video that we just did for 11.6, we talked about we could use a ratio test with an alternating term. But I want to note to you here, right, that when I'm using the ratio test, if I don't have exponentials or factorials, if I only have algebraic expressions like square root of n or n cubed, my ratio test is always going to be inconclusive, right? So I don't want to use a ratio test. Don't use the ratio test, right, unless we have at least an exponential. Right, so we have something like b to the n or r to the n of some form, right? So unless we have exponential or factorial. Right? So in this example that I just wrote, I would definitely not want to use the ratio test here because it will be inconclusive. All right, let's say we have an example like let's say 2 to the n over 1 plus 3 to the n, something like that, right? Going out to infinity. So when I look at this isn't exactly geometric. This behaves like, right? I have 2 to the n over 1 plus 3 to the n. This behaves like 2 to the n over 3 to the n, which is convergent geometric. Right? There's convergent geometric. All right, but this series isn't exactly geometric. So because it behaves like a geometric, I'm going to end up using the limit comparison test. Use the limit comparison test, and I'm going to compare to that convergent geometric series. So just like we saw back up in that prior page, when we had kind of a ratio of algebraic forms, it wasn't exactly a p-series, but it behaved like a p-series. So we use limit comparison test in that case. And then here's another similar example. I have something that's similar to a geometric series, so I'm going to use a limit comparison test and compare to a known geometric series. Okay, another example. Let's say I have something like 2 to the k plus 1 over k factorial, right? Going out to infinity. Anytime I see a factorial, I'm going to use the ratio test. And this is by far going to be the easiest approach. Remember we discussed in 11.6 that when I have factorials or exponential in form, the ratio test is always by far the cleanest type of technique or test to use. All right, so that is really all I wanted to discuss in this video, just discussing strategy of all the prior tests that we've looked at. Now, in the next string of videos, we've got about 4 videos where we're going to introduce the idea of a power series. This is by far the coolest stuff ever. Power series are extremely useful in lots of different realms of science. So we're going to start taking a look at power series in the next couple videos and their applications. I'll see you in the next video.